So this last video is a review of supply chain network design, which is the last major topic in this class and a large focus of the final exam. So the main questions we asked in this class was, where should we have facilities be located? And then how many of them should we have? And then once we have locations, how should we use those locations to serve demand? And then how should supply feed each of these locations? And so those are the decision variables primarily that we looked at in this class. And we thought about network design just to give you some intuition, why this is a challenging problem and why this is interesting. And it really ties together a lot of things that we talk about throughout the class, is just taking something as simple as how many facilities should you have. That's good because we're usually more responsive. We're closer to our customers, and therefore we can get our products quicker to them, or they could get closer to us, which is good, but that decreases efficiencies in that we have usually higher facility costs, we have higher inventory costs, but then we have lower transportation costs. And so this is a good kind of topic to end the course, and that is bringing together many of the different things we talked about throughout the class into that. And you hopefully saw that on your homework 4, where the very last problem, while it required you to solve a network optimization problem, you also had to consider inventory and transportation costs associated with that. So the first network optimization problem we studied in this class was called the set covering problem. And so formally, the set covering problem minimizes the cost of locating facilities from a set of potential facility locations, and it enforces a constraint that all demand locations need to be served or covered, hence where the name comes from, with some pre-specified criteria. So that could be a maximum travel distance. You have to be within 30 miles, 30 minutes from every set of demand locations. You might have to be adjacent to some region, or however you want to define this. But it has to be pre-specified, and the word that I think is really critical and is bolded is the word all. So all demand points have to meet this criteria. So it ignores budget constraints, so it assumes there's enough money to do that. And there are different ways you could think about the problem if that's not the case. But the goal is to ensure that all demand points have met this criteria. So you can think about this problem as an extremely something that Oprah would like. You all get a car, everybody gets a car, you all get covered, right? And so more seriously is that these are applications when equity is important. So you oftentimes see them in public services, locating facilities like EMT or fire stations. It's also used when you want to make sure that everything looks fair. Is fair. So if somebody lives in a certain neighborhood, they should all get the same level of service as another neighborhood somewhere else. So mathematically, how do we formulate that? So we have a set of potential facility sites and a set of customer sites. Sometimes these are the same set, sometimes these are different. So be aware if they're different or the same, keep that in chart. We also know as an input parameter the cost of building a facility at each site J, and then we have this input parameter that's a binary parameter. So it's a piece of data that says, if I build somewhere, will I cover a customer or not? And so hopefully most people use this AIJ matrix in the Pennsylvania homework problem and use an if-then statement. It is an input parameter because we can calculate it a priori given the covering criteria. The variables, which is what we're getting to decide in our problem, is 1 if I build, 0 if I don't. In terms of our objective function, we are trying to minimize the total cost of building. And so that is the sum over, if I build, it's a 1, if I don't build, it's a 0, and then I only pay for places I build. And we have to say that all demand points I have to be covered. And so there's a constraint for each demand point I, and the greater than or equal to 1 means we need to build at least one facility that covers us, and that covering us is however it's defined in the problem. And then also we have decision variables that are 1 or 0. This is a binary decision variable. 0.5 doesn't mean anything, for example. So you have to have either 0 or 1. 0 means I don't build, 1 means I build in location J. So you should be able to formulate those optimization problems with set covering, and you should also be able to solve the set covering model using the greedy heuristic. I won't go through all the steps here, but one thing I think that's worth stating is the formulation, the model, is the same. How I go about solving it is different. So you could go and solve it, putting in Excel and get the optimal solution. You could also go and solve it using the greedy heuristic. And so why do I need this is that if you've taken an operations research course, an integer program or a binary linear program can be computationally challenging. And so for the problems we've done in this class, it's not a big deal. You can solve quite large problem instances, even exactly. But if you go into the world of a huge numbers of things, you sometimes need specialized solution approaches that don't try to solve things optimally. And that's what the greedy heuristic does. So you should be able to use the greedy heuristic. You should also understand what's going on. Like, why are you allowed to delete constraints and things like that through the process. So you should be able to apply it on the final exam and then conceptually understand why does it work. So it gives you always a feasible solution because you're basically making sure each of those set covering constraints are satisfied before you remove them in the iterative process. And so what should you be able to do? You should understand these trade-offs. You should know what the set covering problem is, when it's appropriate to use. You should be able to formulate it as an integer program, an integer linear program, and you should be able to solve it using software, as well as solve it using the greedy heuristic, and then what is feasible, optimal, and kind of all these different properties about the problem. We then also studied the demand allocation model. Here, the decision variables are how much do I ship between a facility and a market. And one thing to note here is we're not actually determining any facilities. So they have been predetermined for us, and we're just allocating how to use the resources. And then we build on that. And so in the capacitated facility location model, we now have how much do I ship between facilities and markets, and whether a facility is opened or not. And so we are adding now the facility location. And remember this constraint here. This one is one that a lot of times people get caught up on. You need the binary variable matched with the xij variable. And so please don't forget that as you're formulating these problems for the final exam. And then we also have the multi-echelon location problem. And so one thing I think that's worth thinking about is what model is appropriate in what situation. And how do you figure that out? Well, you have to think about what are your decision variables, what are your constraints, and then what is your objective function. And so if the problem says all demand points have to have some criteria, you need the set covering. If some problem says, well, I want to minimize my cost of building and transportation, and all demand has to be satisfied, but it doesn't have to be satisfied within like 30 miles, then that's a capacitated facility location problem. So you should understand when to use each of these different models, as well as what kind of model they are. And so that's the first bullet point. You should be able to formulate the optimization models. You should be able to identify the type of optimization model. So is it a linear program, integer linear program, etc. You should understand the properties of these models and solutions. So in general, more decision variables increases the potential for better objective function values, but also increases complexity. And you should be able to use your computer software to solve the formulated models and understand their implications.